workshop on doctrines and vibration. It's been a wonderful half week, almost a week. And we're looking forward to the last two remaining talks. Alexandre Miquel on implicative algebras and first order completeness. Thank you.
So, thank you very much for the invitation. I appreciate it very much. I enjoyed a lot of the talks, at least those I could understand. So I should warn you, I'm a logician. I do bits of category things. I'm still a reluctant categorist because I think it's important to leave the autonomy of logic, not to be absorbed, because a lot of people want to absorb logic, but logic should have autonomy. So, I will start with a slide to recall my main concern in logic, which is the big mess of models in logic. My main problem of logic is that the model theory is a big mess. So basically, you start with sparsity models. So the thing you teach to very young students, so it was very wild, but it's quite a lot missing, a lot of things. But in the 60s appeared the technique of forcing by Cohen to prove independent results, and in particular the relative consistency of the negation of continuum hypothesis was a major output of logic at the time. And from an algebraic point of view, it's equivalent to Boolean valued models of set theory. So basically, in Tarski models, you interpret your formula by truth value 0 or 1. In Boolean valued models, you can interpret your formula by any element of a fixed, complete Boolean algebra. If you are intuitionistic, you can restrict to complete hating algebras, and you get hating valued models. But also, another tradition that comes from the intuitionistic side is realizability, that was introduced in the 40s by Pliny, in which you interpret basically each formula by a set of programs. And during a long time, people were thinking that realizability could only be intuitionistic. I remember the first time I published in 2007 a paper in classical realizability. I had some category guys saying that these results were controversial because we know in category theory that it's impossible to have non-degenerate classical realizability. And of course it's false, as Thomas showed actually. And of course, Krivine fortunately didn't know anything about category theory, so he could design classical realizability. He didn't know the impossibility. Thanks to that, he could rule it out. And basically, he could show that it's not an extension of linear realization. It's really a reformulation. You have to reformulate it completely. It's not an extension. That's very important because from the proof theoretic side, classical logic is an extension of intuitionistic logic. But from the semantic side, you have to reformulate things completely. And basically, you have to embed some negative translation inside. And he interpreted classical proofs, and he generalized Tarski models and Cohen forces at the same time. So now the problem is, okay, we have a lot of notions of truth values, and what is an algebra of truth values? And we have at least 4 candidates. So the first 2 ones are easy because one is an extension of the second one, that is hating algebra, Boolean algebra, a complete one always. But also you can take a partial combinatorial algebra or an abstract Krivine structure, and it's a big mess because you have all that things, and in particular, people of the category side tried a lot of time to abstract things, and basically they came with the notion of triangles, which was precisely designed for that. But here I will present my own candidates that are implicative algebras. So basically we shall see that an implicative algebra that subsumes all the former things is an implicative structure, the algebra of truth values plus a separator, a criterion of truth. So I will also read something that Beno told the first day. And I should say, a lot of people came before me. I think that the first guy is Thomas, when he showed how to incorporate Krivine's realizability into the categorical logic. Basically, you were the one to say, okay, Krivine he's not a crazy guy, but he's not working with partial combinatorial algebra, he's working with ordered combinatorial algebra, and that's the bit of things that says, okay, now we can overcome the limitation to intuitionistic logic. And we, in Montevideo, we start with the first thing, which are ordered combinatorial algebras and realizability, but myself, I had a strong ideas on how to do the things, and then I came with implicative algebras. So, what is it? An implicative algebra, basically, they are based on what I call an implicative structure. Basically, it's an algebra, I think of it as an algebra of types. It's much easier, algebra of types. It's a semantic algebra of types. So basically, you have a complete lattice, and you might think of the ordering as subtyping. For me, it's subtyping, okay? That is, you can see any value here as some kind of set of realizers, and these are just inclusions of sets of realizers. And you come with a binary operation, an arrow operator, and it's monotonic on the right-hand side, antitonic on the left-hand side, as usual. Any people who has worked with subtyping is completely familiar with this rule. And the main strange rule is the distributive one, which says that basically, if you read it logically, the meat is just a uniform quantification. Basically, that if A implies for all x b of x, it's the same as for all x, A implies b of x. It's exactly the same thing, okay? That's the thing of universal quantification. So, very simple definition. Okay, here you have an abstraction of what is the notion of truth value. Now, it's not sufficient because in logic, we not only want truth values, we want to distinguish between what is true and what is not true. So, in Hating algebra, in general, you use filters for that, but it happens that my structure is not a filter with respect to ordering, because the notion of filter has already been taken by ordering, so I change the word filter separator. Okay, a separator is just an upwards closed subset of the structure that contains basically the two axioms of Hilbert deduction system, which I call K and S, and the first one, okay, you recognize the first axiom, I generalized it universally. The second Hilbert axiom, I generalize it universally, I call it S. So basically, you should have Hilbert deduction, and of course, you should be closed under modus ponens to be able to make deductions. And if you take an implicative structure plus a separator, you get an implicative algebra. Yes?
Is there a typo in 2? A, B?
It's possible, yes. Where?
Yes, the C is there.
I should ABC, A, C, B, C, right?
No, on top, the one on top.
Yes, it's a typo, yes, ABA, of course, it's an A. It's an A. Thanks, it's an A, of course. Thanks, I didn't see that one. Okay. It was to check whether you want to. I use this each time I teach. It was so long. Okay, so examples of implicative algebras. The point is that you have tons of implicative algebras in the nature. Complete Hating algebras are particular cases in which implication is defined from the order. The important point is that in implicative algebra, ordering, subtyping ordering, and implicative, the implications are quite autonomous. They have axioms, but you cannot reduce one from the other. But in Hating algebras, you can always define ordering for implication or implication from ordering. That's a particular case when they are completely tight. Of course, complete Boolean algebra is a particular case. But also, if you take a total combinatory algebra, you take the total combinatory algebra, you take your power set, you say that subtyping is inclusion, you take clean a row, and you take the set of all non-empty truth values, and it's a complicated algebra. And also, I will not detail, but you take an abstract Krivin structure in classical realizability. Here you take the set of stats, so you have to think in a reverse way. No, you reverse inclusion, you replace it by reverse inclusion, and basically, it's also an implicative algebra. So, of course, you see that it's basically, I see implicative structures as a form of semantic system F, because I have universal quantification and type arrow. I was inspired by systems a lot. So, basically it's a model of minimal first-order logic in which you interpret implication by the arrow operator and universal quantification by the means. But of course, in these settings, we can recover all the other connectives using the second-order encodings. And this is the way I will use my encodings. See, here I very high Harvard-oriented conjunction. I write it with the times, disjunction with the plus, and here I use the second-order encoding of exist. Okay. So now the manifesto. The manifesto. The manifesto is the following. Primarily, an element of an implicative structure represents a truth value. But the miracle of this is that actually I can also define lambda abstraction and application at the level of truth values. So in particular, we can see each realizer as a particular truth values, because I will embed the lambda calculus inside, but also I can see each truth value as a generalized realizer, because I can apply truth values to truth values. That's the big point, so we get to the ultimate die-hard carry-out correspondence, realizer equals program equals formula equals types. When I saw that, I knew I had solved it. This is in 2011 I realized it, and I said, okay, now I got the thing. Okay, so now we should understand the meaning of this relation below that. If you view A and B as types, okay, it's subtyping. But if you view A as a realizer and B as a truth value, then it's cyclic. And if you view A and B both as realizers, it's reverse definitional order. And in particular, you can understand subtyping as a reverse spot order. Okay, so now here I don't detail this, but you can basically embed the full lambda calculus inside. It's not an embedding because it's not necessarily injective. And as Antonio Salibra, I don't know, he's here, he said that actually if we want good properties, we should not require that it's injective. And basically you have how to encode application in this framework, how to encode lambda abstraction, and then you have the fundamental attention between application and implication. So it's very nice because on the left-hand side, you see these objects are as realizers because you have application, and on the right-hand side, you see them as true values because you have an implication. And what I say is that the fundamental adjunction of HE on the low level, on the assembly level, is based on this adjunction, which is much more low level. Okay, so of course, you can embed all lambda terms, you can encode all the full lambda calculus, and basically, you draw each time you perform beta reduction, and you go lower each time you beta reduce, as usual. Okay, but there are not necessary qualities. And in particular, a particular property of separators is that by construction, separators contain all the lambda terms. That is, basically, they say all proofs are true with respect to any criterion of truth. Because all proofs are true. Proofs are realizers, but they are also true values, but they should always be considered as true. Separator is just a definition to say, okay, all lambda terms are true by definition, whatever the criterion I have. Okay, particular case, completeness algebra. This is a particular case in which implication is defined from subtyping by the usual adjunction. And in this case, you can see that application coincides with the bit. All lambda terms collapse to top, which explains why in forcing we never use lambda terms, because they all collapse to the top value. And in the particular setting, the separator is the very same thing as a filter. So you can see implicative algebras as non-commutative 18 algebras, in which you replace NIT by application that is a non-commutative, non-associative operation. Okay, but in the general case, that is when you are not in the particular case of completeness algebras, in general, separators are not filters, and that's very important because that's exactly the difference between forcing and realizability. That is, in general, when you are outside this slice, that is, when you are not a completeness algebra, the separators are not filters. They are not closed under binary limits. They are closed under application, but they are not closed on limits. They are closed on limits, of course, when they both coincide. And the point is, actually, you can show that you get a forcing model if and only if the underlying separator is closed under limit. Okay, so it's just a rationalization of all the different forms of model. So, some constructions we can do each time you have some implicative algebra. Each time, so here, the big point in logic is that logic, as I understand it, is based not on one ordering, but on two orderings. An intentional one that is subtyping, and an extensional one that is a logical ordering. So how you define the entailment, which is a logical ordering, it entails modulo the separator S, if and only if the implication belongs to the separator. Okay? That is, A implies B if A implies B belongs to the separator is true. Okay, and if you do that, you can show that from the definition I gave to separators, it's a preorder. And when you make the coset reflection of that, you get a coset, you get a Haitian algebra, which is the underlying logic of your implicative algebra. So your implicative algebra is the intentional side. Once you quotient it with respect to the logical ordering, you forget about proofs, you get its extensional reflection, that is a Haitian algebra. That's really the principle of it. So, in practice, the big surprise is that implicative structures or algebras, they can be manipulated almost the same way as complete Haitian or Boolean algebras. I will give some examples. For instance, if you take a product of a family of implicative structures or algebras, it's an implicative structure of algebras, you just define the things component-wise. Okay? But also a very funny thing, which may be big pleasure when they discover it, you also have the analog of ultrafilters that are ultra-separators. It works exactly the same way. So an ultra-separator is just a maximal proper separator, and is exactly the same as saying that when you put the quotient, you get the two-valued Boolean algebra. Beware, here there is a small trap I have not time to explain, but it doesn't mean necessarily that your ultra-separator is classical. There is one example of a non-classical separator who is an ultra-separator. This is clearly separator in clearly realized metric. Just leave it for you. And of course, due to zone lemma.
You mean classical 01 or?
Classical 01, yeah. The 01. But in clearly realizability, that's easy because in clearly realizability, either a formula is realized, either its negation is realized. So when you quotient, you only have two true values and it's not classical. That's a big trick. So if you want classical logic, you need more than an ultra-separator, you need a classical ultra-separator. That's a big, strange thing that I discovered. It puzzled me many months because I did not understand what happened. Okay, and of course, each proper separator extends to ultra-separator. This is an ultra-separator axiom, which is weaker than the axiom of choice, and it's easy to show that it's equivalent to the ultra-filter axiom. That's exactly the same strength. So it's nothing new, that is, we know that it's strictly weaker than the axiom of choice. It's a very weak version of the axiom of choice. So, now, first category, buzzword, triangles. Of course, each time you have an implicative algebra, it induces naturally a set-based triangles. How do I construct it? Okay, I take my index set I. I conform the power implicative structure. A to the I is an implicative structure. Okay, A is an implicative structure, A to the I is an implicative structure. But now I form a special separator, which I call the uniform power separator, which is basically the separator of A to the I that is generated by constant families. That is the separator, or if you prefer, is just the separator formed by all the families whose meat belong to the separator S. It's the same, or it's the same as this formula. Okay, so it's what I call the uniform power separator. It's included into the real power separator, but this one is useless. So now you have an implicative structure, a separator. Now, of this implicative structure, you make a quotient, you get a Haitian algebra. But it's a triangle, of course. It's functorial, it fulfills everything, and actually, if you look at it, it encompasses all the set-based triples known so far. This is just a factorization of all the triples we have in the literature. So in particular, forcing triples, they correspond, or locate triples, they correspond to the case where you have a complete Haitian or Boolean algebra. Then, if you want to use triples induced by total combinatorial algebras, it's a particular case of this construction, if you look at it. And if you want partial combinatorial algebras, it's a bit more complex because you need some step of completion to get an implicative algebra. I prefer to solve the details. It's one of the reasons why Bello wanted to have a larger definition. But actually, you can always do everything with implicative algebras. Partiality can always be replaced by an order. It's something we know since Scott. If you have partial functions, just add the bottom value and put an order. It's sufficient. And also, you can show that the triposes in use by abstract Riemann structures, and here you have to go to Thomas, there are also particular cases about this construction. So basically, and that was a big surprise, to have one construction that factorizes all the constructions we had before. So in some sense, this is the thing that Hyland, Johnson, and Pitts were looking for. This is the algebraic structure they were looking for. Because when they introduced the notion of triples, it was just an intermediate device between Heyting algebras, partial commutative algebras, and toposes. But for me, it was a bug, because it's basically a tripos, it's a model of higher order logic. And you use the class-sized object to model higher order logic. For a logician like me, it's an atrocity. That is, I believe in triposes based on small categories. But based on such a big category of set, no, it's not reasonable. We should reduce the complexity of the field. Because you cannot model higher order logic using a structure that is way above higher order logic. It's not reasonable. In general, you want in logic to keep the same core-theoretic strength. And that was my main complaint against set-based triposes.
Later.
Yes, you have triposes on other categories. But with this one, I have no problems. My only problem is set-based triposes. I just want to kill set-based triposes, not all triposes. Just the set-based one that are useless in my opinion. So actually, the next slide. Now the big question is, do implicative triposes encompass all set-based triposes? And if you have listened to the Bellow's talk, the answer is actually yes. And the main theorem I proved some years ago is that actually using some kind of black magic, you can show that each set-based tripos is isomorphic to an implicative tripos. That is, for each set-based tripos, you can extract an implicative structure. So basically, now you can keep set-based tripos, they are just useless. Okay? But you can keep the other kind of tripos. I have no problem with the other ones. And it's very important because this proof has been done actually by 4 people with a gap of 40 years. Basically, the first part of the proof has been done by Hyland, Johnson, and Pitts in a small part of their paper that nobody read, in which they want to reduce the complexity. They show that the tripos is just characterized by a small set plus some operations, but it has powerful algebraic properties, and then 40 years later I came and I turned their set into an implicative algebra. And this was the solution, yes. So now it's just a way to represent set-based triposes. And we can also show that all set-based triposes are generated by OCAs or OPCAs with filters. They have all the same expressiveness. And now, actually, you can also show that classical implicative algebras, the classical ones, have the same expressiveness as abstract Riemann structure. It's the same as classical realizability. As a corollary, something that few people know, that each classical set-based tripos is a Kevin-Todd tripos. It can be done with classical realizability. Okay, so for me, now I will go to first order completeness. So this is clearly, it was higher order completeness, so now I want to see what happens on the side of first order logic. So, okay, I have to define the notion of implicative model of first order theory. So it's the same definition as usual, you just replace your 0,1 by your implicative structure. Okay. So here it's a A-valued model of a first order long range, L, so you interpret function symbols by functions and predicate symbols by predicates valued in A. Okay? So now, once you get a first order long range and an interpretation of this long range, you interpret terms, first order terms the usual way, don't change, and you interpret formula using the second order encodings for your connectives. This one. Okay. You remark that in order to define this interpretation, you don't need the separator. You just need your algebra of true values. The separator is useless. But of course, if you want to define satisfaction, in the end, you introduce the separator. You say that phi is satisfied in your model M whenever its true value belongs to the separator. Okay? So that basically the generalization of Boolean value models, 18 value models, and Tarski models. Okay, now I will restrict for technical reasons to classical first order theories because I was stupid enough to not be able to extend it to interesting theory. So up to now I have partial results. Okay, my theorem will only hold for classical systems, but I suspect that we can extend it to all intuition systems as well. It's just more technical. I will show you where I have my problems. Okay, so an implicative model of the first order theory is just.
Could you remind us what is the classical implicative algebra?
I never defined it.
Yeah.
Basically, it's something in which the law of excluded middle is true. It belongs to the separator. You write it down, the value, you generalize it for all values, putting a big meet. Basically, it's meet for A plus not A.
As a meet, not with your multiplication.
You can also use the law of Peirce, it's equivalent.
No, but I mean, you do it with the meet, not with the implication.
No.
Not with the adjunct.
It depends, you can do it with the implication if you use the law of Peirce. Actually, I do it this way in my paper. The law of Peirce is equivalent to classical algebra.
Yeah, but then you are in the other process, in your article algebra, right?
The only difference between the law of Peirce and excluded middle is extensible limit, that is free. It's free. So, okay, the notion of implicative model is exactly what you guess. Okay, it's something that fulfills all the axioms. That is, it means that for all axioms, you require that the denotation of your axiom in the underlying implicative structure belongs to the corresponding separator. Okay, so of course, Boolean value and in particular Tarski models of T are particular cases of implicative models, okay, where you have a complete Boolean algebra. And the soundness is obvious. Now I'm interested in some remarks. In the definition of model, the separator is only used to define the notion of satisfaction. It's not used to define the notion of true value. So we can do some kind of patch. We can change the separator on the fly. We can say, if I give myself an implicative algebra with some separator and I extend my separator, I use A colon S prime to say I draw my separator. And actually, I do the same for models. If I have a model of implicative model of some first order language, and if I have a way to increase my separator, then I get a new model which is on the new implicative algebra. Okay? And of course, I keep truth because I increase my notion of truth. So that's important. Clearly, if phi is satisfied in M, then if I increase my separator, phi will be more true in M. It's something, some kind of non-truth. Okay, so now I can state, yes, a technical device. I have to define what is a full model, exactly the same way as in Boolean value models. I will not insist on that a lot, but it's basically equivalent to the criteria of Boolean fullness in Boolean value models. Okay, nothing new. Now I will go to the main theorem, that is, how to go from a classical implicative model to a Tarski model. Okay, I assume given an implicative structure, and I recall what is an ultra separator. It's a maximal proper separator, or equivalently a separator such that the quotient is 2. Okay, of course, in any implicative structure, any consistent separator can be extended into an ultra separator. So, now, if I take a full and consistent implicative model of first order theory T, each time I have, yes?
Is the implicative structure the same as implicative algebra?
Implicative structure is the implicative algebra without its separator.
Without the separator.
Without the separator. Okay, that's the algebra of two values. Okay, for people, implicative structures equal first order language. Separator is first order theory. That's just it. If you get it, we will see we have a one-to-one correspondence. We have a correspondence between both. Actually. So, when T has an equality symbol, of course we are. What I wanted to say before is that if you have a full and consistent implicative model of some first order theory T, then each time you increase your separator into an ultra separator, you get a Tarski model. Here, important to not have equality, because if I have equality, I also have to make some quotient inside the model as usual. I prefer in this talk not speaking about equality, which is always a problem. We know that. Always a problem. I put it aside. I consider equality as a non-logical symbol. Okay. So now, my strong completeness for implicative models. What I say that for each first order language L, there is an implicative structure together with an A model, which is actually a syntactic model, in which a formula phi is a tautology in this language if and only if its denotation belongs to the classical core of the structure, which is the smallest classical separator of this structure. Okay, moreover, if I have now a classical first order theory on the language L, then I can find a classical separator such that for all phi, T proves phi if and only if the denotation of phi belongs to S. And it's always if and only if.
How do we know that there is such a classical core?
You can always take the smallest separator generated by something. You can generate always a separator by any set of values. You just take the intersection. Oh, it's implicative, sorry. You take the intersection, it's implicative. But you know, I have a complete lattice. Complete lattice is already implicative. It was my failure.
The triples are not.
Yeah. So, actually, I should say that I knew that, but Louis gave me a simpler proof that the strong completeness theorem already holds for Boolean value models, which are particular cases of implicative models, which means that this theorem is nothing new. It's completely well known because it's just saying, I want to find an implicative structure, but I already know that there is a Boolean value model, which is a particular case of implicative model. But what I will show is that there is an interesting new proof of it, and that the construction will keep the computational contents of the proofs. This is what I want. I want to keep the computational contents. Okay, so I will give a more proof theoretic, more realizability argument of the proof. So now I give a sketch of the proof. Okay, I start with system NK, natural deduction to classical logic. And I used a very simple language based on falsity, my predicate symbol, my first order terms, implication, and for. And now is the reason why I'm classical, because up to now I'm not able to deal with other connectives. In classical logic, it's not a problem because we can define all connectives in terms of this. But in intrinsic logic, it's not a complete set of connectives. That's the only reason why I use classical logic. Okay? Okay, that's it, my reason. The day I will be able to add a primitive conjunction, primitive disjunction, primitive disjunction modification, and get rid of this field, but you will see that it will be a nightmare in a couple of steps.
But what is that complete?
Because in classical logic, you can always define any collective, any collective in, from this, and this, using the Morgan laws.
But I mean,
Let's go on, because we have only 2 more minutes.
Yeah. So, now, first thing, I extend my language. Now, okay, carry Howard, there are types. Forget about formulas, there are types. I add top type, intersection types, and now it's a big homage to the Italian school about subtyping and intersection types. Here, thank you very much for all the people who have contributed. You helped me a lot for this theory. Okay, I have this type system. First, I add a subtyping relation because I need it. Okay, here, look at the subtyping. The only new feature I add, this is an idea of Olivier Laurent 2012, which is to present subtyping not in a natural deduction style, but in a sequent calculus style. That is, instead of having introduction rules and elimination rules, I put left and right rules. What is the difference? Here, the reflexivity has a strong flavor of axiom rule. And the transitivity has a strong flavor of the cut rule. Yeah. And as we all know, the cut rule is admissible, we can drop. This rule is admissible. You have a cut elimination for subtype. Okay, it was shown by Olivier Laurent, but only in the propositional fragment. I just added universal quantification, first order quantification, it works as well. Okay, once you have that, you can add proof terms. Here you have classical proof terms. Okay? So here, variable, lambda, application, and call CC. I need call CC for classical logic. Okay, I will go up to 25. I said in the beginning, 25. Okay, here are the rules for proof terms, nothing new. Okay, something that we already know. Okay, now I have that. I want to make a Kriving machine for that. So I need to extend again my proof terms into C terms. I need to have paraproofs inside, continuation constants, to have stats and processes. Here, first before, I have to observe that this calculus, despite the presence of intersections, is a conservative extension of classical logic. Logical is conservative. That's something I never saw mentioned. If you take a type with intersection types, you replace, it's clear that intersection is definitely not equivalent to conjunction. But if a formula is with intersection is derived on the system, and if you replace all the intersections by conjunction, then you get another proof of this formula in classical logic. It's a conservative extension. The proof is very easy. It was a big surprise. Nothing fancy. Okay, I think nobody observed it. This is the only reason. Okay, so it's a conservative extension. It's very important because it says that if I have a proof term here, if and only if I have a derivation, I want if and only if I want conservative all the way down. Okay, now I take the full Kriving machinery. I extend my proof term with continuation terms. I add a diamond that is a paraproof for all formula. I add continuation constants. Now I have stacks whose bottoms are parameterized by atomic formulas different from top. There's a lot of machinery here. And you have processes in the same way as Kriving. And now you have a lot of typing rules for C terms, for stacks, and for processes. And thanks to the presence of intersection types, I have both subject reduction and subject expansion, both for C terms, stacks, and processes. And even I have closure under evaluation and also anti-evaluation for the processes. Okay? So now I have all of this with subject reduction and expansion. Now, let's consider the closed processes. The set of closed processes is closed under evaluation. The closed type processes. But due to intersection types, it's also closed under expansion. Now, if you are a Kriving guy, you have a set of processes that is closed under expansion. What do? You build a realizability model whose call is precisely the set of all well-typed closed processes, because it's closed under expansion. Of course, you define falsity values and truth values in order, so you take the set of all closed well-typed processes. Here, of course, you take the Herbrand universe as first-order model. Yes, I need to assume that I have infinitely many constant symbols in my language. If I don't have them, I have. Okay? It's a usual conservative extension. Okay, here is the definition in the model of the falsity value, definition of truth value, and by construction, I did the thing in such a way that all realizers are well-typed. That is, all the realizers are well-typed, and all the counter-realizers are well-typed too. But in realizability, we also have the adequacy lemma, which says that also everything that is well-typed is a realizer. So I will take the exact equivalence between the typing and the realizability. I got a realizability model that coincides with closed well-typed terms, stats, and processes. Basically, I got what I wanted, that is to determine the frontier between. Of course, it's an implicative model. This thing is an implicative model. Each classical realizability model is a classical implicative model, and I got the frontier between syntax and semantics. This is exactly what I wanted. Something where you extend your syntax. This is what you do when you do first-order completeness. You extend the thing, you complete the things, but now I do it at the level of proof terms in such a way that you are so much complete that you coincide with your own realizability model. And the only thing you have to declare to the customs is that your terms are closed. That's the only thing. So you don't have the right to embark in your language 3 variables. That's the only limitation you have when you go from syntax to semantics. So, of course, when you have that, so the above proof sketch so that any first-order language can be turned into an implicative model in which you have that. And the implicative structure is just derived from the set of stats of system, this system, type system. The underlying separator is generated from the proof terms of system due to conservativity. I will not detail that, but it's due to conservativity. And actually, the first order model is just the Hermann universe as usual. Now, if you want to incorporate the axioms of first order theory, you just fill in the separator with exact axioms, and this works because the separators fulfill a deduction theorem which is the same as for deduction. And this is why you never add too much things, and you get the equivalence. So morality is that an implicative algebra is just the first order theory expressed into semantic terms. This is exactly what I wanted. That is to learn syntax and semantics to see where they meet exactly. So now I can deduce first order completeness. From the strong completeness, I can capture my theory into an implicative model. Then I can extend my thing into if my theory is consistent with an ultra separator, and then I factorize the first order theorem of completeness with an equivalence logic proof on the left hand side, and an implication on the right hand side, and the first one is constructive, so the second one is the ultra iterative. Okay, which is the usual way. It's another way to constructivize the first order logic theorem. And I think conclusion, so just this simple structure of factorized model theoretic construction underlying forcing realizability. It's higher order complete in the sense that it captures all set-based triplexes. But now it's also first order complete in the sense that it captures all theories plus the underlying computational contents using the first order system. And so the result itself is not new, but the proof technique is, and in particular, we capture the computational contents and proofs that is preserved in the implicative algebra. So, and to conclude, because I'm in the category thing, I had to conjecture, of course, is extends to intuitionistic logic. I just have to enrich my type system. It will be a pain. Okay, and to conclude, we know that first order hyperbolic trees are the same as multi-sorted first order theory. Here, multi-sorted is very free. I checked it out. It works very well. So, in some sense, can we deduce that all first order hyperbolic trees are implicative? And I will leave the conclusion for this question. Thanks very much.
Time for a quick question.
Just a comment.
Really?
That I like Typosis, and I think that it is a powerful tool because it deals with my predicative theories, with arithmetics and everything. So that's what. And also because I can handle very well equality. But we discussed
Okay.
with the completeness, strong completeness with equality,
Okay.
which I teach in the first 4 years logic course here in Padua.
Okay.
Thank you.
Good questions. You're next.
So what do you mean by the last item? Because every implicative triangles has a generic predicate, but not every first order item.
I don't need a generic predicate. I don't need a generic predicate. It's a completely different construction.
But what do you
The
mean by
point is that
implicative then?
the point is to give a meaning to this sentence. I still don't know how to give a meaning to this sentence.
Okay.
So it's just
That was my question.
work in progress. It's the part work in progress.
Okay, let's thank the speaker. We now pass the chair.